Let's start. So we're going to continue with our series on recurrent neural networks. And today we're going to be talking about stability analysis and LSTMs. So the story so far, we found that if you want to analyze time series data, then iterated structures like convolutional neural networks are good for analyzing time series with short-term dependence on the past. On the other hand, if you want long-term dependence, where you must consider the infinite past to make any prediction, then you want recurrent structures. So these recurrent structures are recurrent neural networks. Now, the way we presented recurrent neural networks, they were only good for analyzing time series, where you had a great amount of dependence on the past. But what about other kinds of regular problems? Let's see how they can apply there as well. Now consider this simple problem. I want to add two binary numbers. And suppose I wanted to create a network that added two binary n-bit numbers, and I told you, for instance, that the MLP is restricted to being 4 layers deep. How large would this MLP be, based on what you remember from the second lecture? Anyone? Does anybody remember this? How large would this network be? If you wanted to build a network that would just take in two binary numbers and output the sum. Anybody? Unless you want me to begin calling up people by name, I'm waiting for a response. So 2n, n plus 1. Is that how large a network would be for adding two n-bit numbers? Anybody else want to take a guess? Or a fixed number of layers, Mariam? How large would it be? Say 3 layers. How large would it be? 3n plus 1 for a fixed number of layers. Was that 3n plus 3n minus 1? Anybody else remember? We didn't actually address addition. But take a guess, right? What you're going to need is a network that can consider every possible pair of input patterns and generate the output for it, right? So that's going to be big. Okay, in terms of training data, how much training data would it need? Can someone guess? Guys, this is disappointing. You've been through the quiz, you've been through the second lecture, and you can't answer this. 3n. So 3n minus 1 training instances. Would you be able to learn how to add two n-bit numbers after just seeing 3n minus 1 training instances? All possible combinations, right? How large is that? How large is that? Anybody? 2 raised to 2n, right? It's going to be, the model is going to need an X. Remember this, addition is basically an XOR, right? Yes or no? You remember your Boolean arithmetic, right? So addition is an XOR, yes or no? Yes, okay. And how large did we say an XOR network had to be? It had to be exponentially sized, correct? And the input. So if you had a fixed depth. So, and moreover, if you wanted to train this network, because of the completely bizarre manner in which the XOR works, you'd have to see every possible combination of inputs to learn how to add every possible combination of inputs. So the amount of training data is also going to be exponential in n. That makes sense? Yes or no? Right. So, and say somehow you magically learn to build this network. that could add two n-bit numbers. Would you be able to add two n plus 1 bit n-bit numbers? Yes or no? Would you be able to add? No, right? Okay, so now suppose I go ahead from this and say, I'm going to use instead a recurrent neural network. Then how large would the network be for the same problem? How large would the network be for the same problem? Okay, let me give you the answer, right? The recurrent network just has to be this. You can add it 1 bit at a time. All it needs is this recurrent structure, which takes in the current bit from each of the two input numbers and a carry, right? And it's going to generate two outputs, and the actual bit output and the carry. How big would this one be? This is going to be very small because there are only 8 possible combinations of carry and the two inputs and 2 possible combinations of the outputs. So you're going to need a network which needs to remember 8 patterns. That's it. And that is going to be at most 8 units, even if you're very, very sloppy about it, right? Yes or no? Over here. Did this make sense? Right. And how much training data would you need for this? Would you need to see all 2 raised to n combinations, or would something far lesser work? N log n, the patterns, there are only 8 possible input patterns, right? So you're going to need no more than 8 training instances, correct? With just 8 training instances, you should be able to know everything that you can do in the best case. Yes or no? Right. And so here we are, this situation, right? And moreover, because it's recurrent, this, it's not, why? Because there are 3-bit inputs. So how many possible input combinations can you have, Mario? Right. So 8. So that's it. And so the amount of training data required is also going to be very, very small as compared to, and moreover, a network that you've trained on n-bit inputs is not restricted to adding n-bit inputs because it's recurrent. You can, once it learns what to do, it can add inputs of any size. Or here's another problem, the parity problem, right? I want a network that looks at n-bit inputs and outputs of 1 if the number of ones in the input is odd, and a 0 if the number of ones is even. So in this case, if I want to train an MLP, how large would this MLP be? Anyone? How large is this going to be for an n-bit input? So I get one answer. What about the rest of you? What do the rest of you think? How large would this be? Come on, guys. We've got to be better than this. 2 raised to n, right? Because it's an XOR network. We explicitly saw this problem in the second lecture. You can't forget within 4 weeks. And so, and how many training instances would you need to train the network, even if you had the network of that size? You'd have to see every possible input pattern to learn them all, correct? So it's going to be exponentially large, both in size and in the amount of training data. Now, if I did this with a recurrent network, how big would the network be? Any guesses? It's going to be, this is all I need to do, right? The current bit and what the previous output was, that was it. So there are 4 possible combinations. That's all I need to know. If the previous output is 1, and if the current input is 0, I haven't changed the number of ones, so the output remains a 1. If the previous output is a 0, basically the output doesn't have to change, right? If this is a 0, then the output remains the same as what came in on this line. If this is a 1, it has to flip. So there are only 4 possible combinations. This unit doesn't need more than, 4 neurons possibly. And how much training data would you need for this? To train this unit? 4 instances, right? Because there are only 4 possible inputs. And so in the best case, only 4 instances. And it generalizes. If you train it on n-bit inputs, it can still work on n plus 1-bit inputs. Did this make sense? Yes or no? Right. So it's beautiful, right? Recurrent networks are much more powerful than you would imagine. And so here is my first quote. Can you guys see the poll? Okay, 15 seconds. All right, let me end the poll and share the results. So here's what all of you guys thought. Let me stop sharing. So can you tell me the answer to the first question, true or false? Some prediction and classification problems. Yeah, we just saw this. What about the second one? True or false? Also true. And so recurrent neural networks are incredibly powerful, just so long as you know how to use them. And that was the point I was trying to make with this little lesson. Both are true. And so the story so far, recurrent networks, structures that can be trained, can be used to analyze time series data. And even for data that are not time series, they can be really good at reducing the amount of training data and the computation if you can find recurrent structures within the operations. Now, also, we saw that recurrent structures can be trained by minimizing the divergence between the sequence of outputs. So Isaac, the slides should have been up. We've been slow. Their TAs are putting them up. They should be up. If they are not up already, they should be up shortly, right? So anyway, so we also saw this. Recurrent structures can be trained by minimizing the divergence between the sequence of outputs and the sequence of desired outputs. And this difference can be back propagated to compute gradients, and you train the network using gradient descent. But then let's look at something else that's important, the behavior of recurrence. Let's return to an old familiar model. This is the convolutional neural network, which is analyzing a window of the input to make the next prediction, the first thing we saw. Now, in a model of this kind, if the inputs are bounded, they're all finite in value, will the output ever explode? Or will the output also be bounded? What do you think? All the input values are bounded. Will the output stay bounded or will it blow up? Anyone, guys? I have one answer. What about the rest of you? Right? The weights are, well, you're going to assume that the weights are all bounded, right? So if the weights are bounded, here's what happens. These things are bounded. The affine terms here are bounded. The derivatives, the activations don't blow up. So the entire process is going to stay bounded, which means this kind of system where it's what is called bibostable. Bounded input, bounded output. It has bibostability. This making sense? Yes or no? Okay, right. And okay, what about this guy? Will this be bibostable? What do you think? The recurrent network. Any opinions? Do me a favor, guys, just do respond because I'll wait for you. And if you don't respond on time, this class will not end today. So please, okay? We can't say, we cannot say, right? So, well, if the activations are bounded, then, for example, if you use only sigmoid activations everywhere, it will be kind of bounded, but it will saturate. So, and become meaningless. So if we consider other kinds of activations, then it will actually be unbounded. And let's see why, right? To analyze this, it's sufficient to analyze the behavior of this recurrent here, because that's where you get potentially infinite computations. And so let's analyze this recurrent layer and see what happens. And now this is a very nonlinear function because you have nonlinear activations everywhere. And it's very hard to analyze very deeply nested nonlinear functions. So we're going to back off to something simple. The famous streetlight effect that we've alluded to in the past. You can't search in this dark bar, so you're going to look under the streetlight where you can see things. We know how to analyze linear systems. And so we're going to assume that this is a linear system. What I mean by a linear system is that every cell over here has an identity activation. So at any time, the affine value at any of these hidden neurons is simply the weighted sum of the previous hidden state and the current input. And the output is the affine value itself. So is this recurrence with linear identity activations clear to you? The simplification I've just made. Right? Okay, so let's analyze this. Okay, here's what we had. HK, because H was the same as Z, right? Identity activation. So HK was WH times HK minus 1 plus WX times XK. WX is the weight matrix that applies to the input. But then HK minus 1, this guy itself was WH times HK minus 2 plus WX XK minus 1. So let me plug this guy over here. And so you're going to get HK equals WH squared times HK minus 2 plus WH times WX times XK minus 1 plus WX XK. So is this making sense? Yes or no? Right here, okay. And just continuing this, here is what you're going to get. HK is going to be the series where the 0th input is multiplied by WH raised to K. The first input is multiplied by WH raised to K minus 1 and so on. I just got this by recursively expanding this guy. And again, is this making sense? It should, just intuitively it should. You can work out the math. But because I want you to get this because I'm going to analyze this, okay? Right, and now here's the thing. I only need to focus on what happens here. What happened to the input at time 0? If the input at time 0 blew up, then the output has blown up. If the input at time 0 did not blow up, then clearly the input at time 1, which occurred later, could also not have blown up. And so the entire response could not have blown up. Right? That making sense? Right. So it's sufficient for me to analyze this guy, the response to an input at time 0. If this does not blow up, then the responses to later inputs will also not blow up. So this guy is not going to blow up, right? What do I mean by blow up? Virano, we will see, okay? So blow up meaning it just explodes, goes to infinity. But we'll see how that happens, right? Or other things can happen, nasty things can happen. So I'm going to analyze this a situation where I have a single input at time 0. I'm assuming no initial state. This is like having some inputs in the previous time, so I can ignore it, and no further inputs later on. And so let's see what happens to this. I'm going to consider a single scalar case, ht equals w times ht minus 1 plus c of xt. Everything's a scalar. If all I had was an x0 and all the subsequent inputs were 0, then the response at time t is simply going to be w raised to t times cx0. This making sense? Over here. Guys, is this right? Okay. So what can you tell me about the response at time t? If I give you a single input, which is just 1 at time 0, what will happen to the response at time t? Is it going to stay at 1 or thereabouts? If this is 1, will this always stay close to 1 or, generally stay bounded and continue to carry information? Yes or no? And it's going to be times w raised to w times t, right? So what happens if w is greater than 1? What will happen? What happens to it? It blows up, right? Goes unbounded. This is what I meant by blowing up, right? What happens if w is less than 1? I like that. So what happens if w is less than 1? Bounded? It just goes, vanishes to 0, right? And so here we are. The response to the system only stays stable when w is 1, right? Now, what about, this is for a scalar recursion. What about for vectors? Because we really deal with vectors, right? In the case of vectors, we would still have the same thing. H of t is w times ht minus 1 plus cxt. If I just had a single input at time 0 and no further inputs, you're going to get h of t is going to be w raised to t times cx0. This is the same equation as before. This making sense? This guy here? Right. So let's see what happens here. Let's consider w. Using eigen decomposition, I can write w as u lambda u inverse. This is just standard eigen decomposition. You're all familiar with eigen decomposition, right? Right. So, and lambda is a matrix, diagonal matrix of eigenvalues. Okay. And I'm going to assume, without loss of generality, that lambda 1 is the largest eigenvalue, lambda 2 is the second largest, and so on. So this making sense? Yes or no? Yeah. Okay. What happens if I multiply lambda w with itself? If I multiply w with itself, you're going to get u lambda u inverse, u lambda u inverse. And the u inverse u in the middle is going to just do the u inverse and u will cancel out. You'll end up with u lambda squared u inverse. More generally, w raised to t is simply going to be u times, lambda raised to t times u inverse. And this lambda raised to t is simply a diagonal matrix where all the diagonal entries are the individual eigenvalues raised to t. Is this part of it making sense? Okay. I can pull out this largest eigenvalue out here and say lambda 1 raised to t times u. And so now this guy is going to become 1. And all of the other things are going to be lambda 2, lambda over lambda 1 raised to t. Whatever lambda 2 over lambda 1 raised to t, lambda 3 over lambda 1 raised to t, and so on. This making sense? And as t increases, what happens to these secondary diagonal terms? What will happen? They will all vanish because every one of them is less than 1, right? So the only thing that remains is going to be this guy, correct? Yes? Okay. So what can you tell me about the response of this system as with increasing t? So this is what we have, right? For any input for large t, the length of the hidden vector will expand or contract to the tth power of the largest eigenvalue of the eigenmatrix. Do you agree with this? Yes or no? So what happens if this largest eigenvalue is greater than 1? Blow up. And what if it's less than 1? What if this largest eigenvalue is less than 1? It's going to shrink and vanish to 0, right? If this magnitude is greater than 1, it will blow up. Otherwise, it will contract and shrink to 0 rapidly. And so here's what we get. I have some simulations where we just gave a single input of all ones at time 0. Here, lambda max was 0.9, 2 different cases. And you can see how, boom, it always goes to 0. This is lambda max 1.1. It blows up. Only if lambda max is 1, magnitude is 1, it kind of stays stable. These two are the same case. What do you think the difference is between the two? Anybody? What is the difference between the two? This has, remember, when you perform eigen decomposition, the eigenvalues can be complex. They can occur either as real values or complex conjugate pairs. When they occur as complex conjugate pairs, you're going to see some kind of oscillation. Otherwise, you're going to see a smooth blow up, or a smooth response. That makes sense, right? But regardless, here's the thing. So these are complex eigenvalues. These are real eigenvalues. But in every single case, in linear systems, the long-term behavior depends entirely on the eigenvalues of the recurrent weights matrix. If the largest eigenvalue is greater than 1, the system will blow up. If it's less than 1, the response will vanish very quickly. Complex eigenvalues will cause some oscillatory response, but with the same overall trends. Magnitudes greater than 1 will cause the system to blow up. Those less than 1 will cause it to disappear. And the rate of blow up or vanishing depends only on the eigenvalues and not on the input. Is this making sense? Yes or no? Right? Okay. But that was for nonlinear, for linear activations. What happens with nonlinear activations? So here I've replaced the same thing as before, but now I put a sigmoid activation. H of t is a sigmoid of WHT minus 1 plus CXT plus B. Okay. So I have 3 rows and 3 columns. There was no pole here. So the top row is weight 1.1. Second one is weight is 1. The third is weight is 0.9. And within each picture, there are 5 plots. They represent 5 different values of the bias as shown in the figure. And then the 3 columns represent 3 different initial values of x, minus 0.5, 0, and 0.5. Okay. What do we see? And the x-axis in each case represents time. What do we see about the responses in the 9 plots after, say, time t equals 5? Are they different or are they all the same after t equals 5? So what does it mean? What does the long-term response of this recurrence depend on? It doesn't depend on the weight. For the different weights, the responses are the same, correct? It doesn't depend on the input. For different inputs, the responses are the same. The long-term response of the system only depends on the bias. This is if you use a sigmoid activation. I get something very similar. If that makes sense, guys? Yes or no? Right. And so, same thing. If I use a tan H activation, I get much the same response. Here, it also has some dependence on the weights. It depends on the weights and the bias. But so what we will find is that within each row, the long-term response is the same, meaning each row has one weight and different biases. And you're going to see that within each row, the long-term responses are the same. There may be differences between the rows. So what you will find is that the final value depends only on the bias and the weights, but not on the input. Although, in the sigmoid, it hits saturation in 5 time steps. In the case of tan H, it takes longer, which is why in recurrent neural networks, we typically use tan H activations in the recurrent layer. because they take longer to saturate to their default value. Does that make sense? Yes or no? Right. Okay. With ReLUs, things are horrible. ReLUs are basically like linear layers, except it's one-sided. So things will either blow up or simply vanish and go to zero. It's never going to retain anything. So ReLUs are absolutely useless in recurrent networks. Now, this is for scalar recursion. If I look at vector recursion, where these h's and x's are vectors, then I have a similar plot. Here I have a sigmoid activation. So the top plot is when the first input is all ones. The bottom plot is when the first input is all minus ones. And so the two differ in the initial input. And what you will find is that in both cases, if you look across the sigmoid activations, that the vertical axis scales are different. But what you will find is that the long-term response is the same in both cases and depends only on the bias. In the tanh, the long-term response is the same in both cases and varies with both the weights and the bias, but not on the input. The ReLU activation is useless. So what do I mean by saturate? Saturate hits its final value, like this guy. This is the pattern it took. And this is the pattern it's going to take regardless of the input vector. That makes sense? If you have a bias of 0.5, it took 5 time steps to get to the final response, 1.6. For a bias of 0.25, it took this much time, and so on. Okay. So this was with the maximum eigenvalue of W at 1.1. If here I have the same thing with the maximum eigenvalue of W at 0.9, and you see that these two plots are different. But the key thing is that, the upper rows and the lower row are identical in every case, which means that there are differences. Things change with the eigenvalues of the weight matrix. Things change with the bias. Things do not change with the input, which means that the long-term response of the recurrent layer depends only on the weights, the eigenvalue of the recurrent weight matrix and the bias, but not on the input. Now, if you want to look at perform a formal stability analysis, you'd have to do you can go through the math, and you need to consider convergence of Lyapunov functions, Roots criterion and whatnot. But even the math will tell you the same thing. Bipolar activations like tanh take the longest time to get to their useless default behavior. Others get there faster, but in every case, the final value of the system in response to an input at time 0 is going to depend only on the eigenvalues of the weight matrix and the bias. And the best case memory of what was the initial input is very short. What the initial value was is forgotten exponentially quickly. Is this making sense? Yes or no? What about the rest of it? Okay. I'm getting 6 responses from 6 people. Maybe I should wait for a thumbs up from up to 50 people, which is what I used to do in the past. Just give me a thumbs up, I can count them, and then I can see how many of you are responding. But here's a poll. I assume you can see the poll. Fifteen seconds, guys. Okay. Give you 5 more seconds and stop it. And the poll. Here's what all of you thought, but let's ask you, explicitly. For the first question, which are the true statements? Select all that are true about how long, how many time steps. And RNN can retain some of the memory of the input pattern. Only the first three. Depends on the weights of the recurrent layers. It depends on the bias of the recurrent layers. It depends on the activation of the recurrent layers, but it does not depend on the input. What about, so this is the length duration of memory, right? What about what is exactly remembered? Even that only depends on the weights, bias, and activation. It has no dependence on the actual thing you're trying to feed in. So are either of these behaviors useful if you're trying to analyze long-term patterns? What do you think? Is this how, do you think this is kind of useful behavior? Or would you rather have, no, right? You basically want the network to remember things until it is no longer required. And what is remembered and how long it is remembered must depend on the input and not the parameters of the network. And that's not what happens here. So recurrent networks retain information from the infinite cast. In principle, in practice, they tend to blow up or forget, depending on the largest eigenvalue of the recurrent weight matrix. If it's greater than 1, the response may blow up. If it's less than 1, it may die. And what is remembered? The memory of the network also depends on the parameters and activation of the hidden units. Sigmoids activations saturate, and the network becomes unable to retain new information. ReLU activations either blow up or vanish. Tan-H activations are slightly more effective than sigmoids, but still not for very long. Right. So is everybody good with this lesson so far? Yes or no? Right. Give me a thumbs up, guys, so I know that you can. Right, okay. So here's where we are. RNNs are excellent models for time series in theory, for time series prediction, classification, sequence generation. They can even simplify problems that are difficult for MLPs, as we saw. But the memory is terrible. But then we also have an additional problem, right? Now, this problem is not just a problem for RNNs, but for any deep network. This is true for any deep network, not just recurrent networks. The gradient of the divergence, the loss with respect to the parameters, is unstable. What do I mean by this? So here is what a typical deep network looks like. You have some inputs. No, this is true regardless of whether it's CNNs, RNNs, or whatever. They're just very deep networks, right? Even a CNN is scanning with an MLP. And so if you have a deep CNN, the MLP is just going to be, yeah, exactly, Miguel. And we'll see why, right? So eventually you just have a very deep network. So the output of the network is going to be a function of the output of the penultimate, the output of the final layer of the network is a function of the output of the penultimate layer, is a function of the output of the previous layer, and so on. So the final loss is going to be a function of the output of the network. And so we saw that if we draw the sequence of influences, this is what it looks like. The input X influences the first affine term Z, and the Jacobian of this influences the weight matrix, first weight matrix. Then the affine value influences the activation value, and the the weight of the influence is the Jacobian of the activation function. This output influences the next affine value, where the Jacobian is W2, and so on. So do you guys remember this from, I think, lecture number 4? Yes or no? Right. So when I compute the derivative of the divergence going back, what do? I first compute the derivative of the divergence with respect to the output of the network, which is nabla D. And then each time I take a step back, what happens to the derivative? How do I modify the derivative? If I take the derivative here and back propagate it here, what did I do? Anybody remember? What did we do when we took a back derivative from here and moved it here? Anyone? You've seen the lecture, you've been done the homework. So So chain rule, right? What happened was this, guys. You have to do this every time when we moved back here. We just multiplied this derivative by this Jacobian. Remember? Then we moved it back here. You multiplied this derivative by this Jacobian, which happened to be the weight matrix. Then you take a step back. So each time you take a step back, you multiply by the Jacobian that's on the edge. That's how the back propagation happened. Do you remember this? At each step, the back propagation was just a simple right multiply. Right. I see a single thumbs up. Can I get 50? There are 200 people in class. I'll wait for at least 25, please. Okay. So this is what happens, right? The derivative of the divergence with respect to the output or output of the kth layer, somewhere in between, is just a sequence of right multiplies of Jacobians and weight matrices. All of these are matrices. Both the weight matrices and the Jacobians are matrices, right? So first, let's analyze what happens when you pass the derivative backwards through a Jacobian. Now, for any layer, the Jacobian is typically just a sequence of activation, a vector of activation functions, independent activation functions, right? And so we saw that if you have a Jacobian, so this is regardless of whether it's a recurrent network or any other kind of network, the Jacobian of the activation, because each neuron is working locally, the Jacobian itself was a diagonal matrix, except for the final output layer, or if you have a softmax where you had a full matrix. But the Jacobian tends to be of this form. Do you remember this? When you take it past an activation, right? And what are the individual terms of the diagonal? What are they? These terms. Anyone remember? These are just what are these guys? What are these? This is going to be the derivative of the activation functions, correct? These are the derivatives of the activation functions. This is the derivative of the activation function for the first neuron in the layer. This is that for the second neuron in the layer, and so on. And what do these derivatives look like? So each of these terms, if for the tan H activation, depending on the input, the derivative looks like this. When the input is 0, the derivative is 1 at all other inputs. For all other values of z, the derivative is less than 1. For sigmoid, the derivative is always less than 0.25. For ReLU, the derivative is either 0 or 1. So I have a matrix where the diagonal entries are all 1 or more generally less than 1. What happens to a vector if you multiply it by a diagonal matrix where the diagonal entries are 1 or less? What happens to it? Can anyone tell me? What would happen to a vector if I multiplied it by a diagonal matrix of where the diagonal entries are less than 1? It's going to get strictly smaller, right? It's going to get best case, it's going to stay the same length. Otherwise, it's going to get smaller. So each one of these guys is going to shrink the derivative in size. Do you see that? Yes or no? Right. So what about these guys, these weight matrices? What happens when you multiply a vector with a matrix? Do you guys have any idea? I'm assuming not. It doesn't always get smaller. Each weight matrix is going to have a bunch of singular values and corresponding singular vectors. Some of the singular values are going to be greater than 1. The majority of them are going to be less than 1. This is just a property of any random matrix. And now, when I multiply a vector by a matrix, then the vector is going to grow longer along the directions where the singular values are greater than 1. And it's going to shrink in directions where the singular values are less than 1. Is that making sense? Over here? And so what about the rest of you guys? Do you see this? If I multiply a vector by a matrix, then the vector has components along the singular values, singular vectors, and the components along the singular vectors with singular value greater than 1 are going to increase in length. The rest of them are going to shrink in length. But what happens is that, but this vector, a vector goes past this guy, and some components will shrink and others will expand, but then it goes past the Jacobian and everything gets changed. So the components that may have expanded over here when it went past here can end up in a direction after going through the Jacobian where for the next matrix, they are in a direction that's going to shrink. So even the few components that do expand in any weight matrix, any random matrix, the majority of the singular values is going to be less than 1. And so as you keep multiplying backwards, most directions will shrink. But because of the intermediate behavior of this Jacobian, you actually have to look at this big entire Jacobian weight matrix block. You're going to find that as you keep going backwards, at each step, this multiplication by this block is going to expand nabla-d in some directions where the singular value of this block is greater than 1 and shrink it in directions where the block is less than 1. And also because when you go from here to here, the vector has been transformed a bit. The directions which have singular values greater than 1 for this block may be different from the directions where the singular values are greater than 1 for this block. So as you keep going back, eventually the derivatives are going to keep shrinking, except in a very, very small number of directions. And so eventually the derivative this is going to result in insignificant derivatives in most directions and a small number of directions where the derivatives are going to blow up. Does this make sense? Yes or no? Right. So you have the problem of exploding and vanishing gradients. Just for visualization, here's an example. This was an MNIST network. It's 19 layers. Each layer is 1024 units wide. So actually this text is wrong. I'm showing you the derivative with respect to the output of each of the 1024 neurons, starting from the output, going back to the input layer. And what we find is that this is at initialization when the derivatives are the largest magnitude. The derivatives, if I use ELU activations, the derivatives have decent magnitudes at the output layer. But then when you go back just 5 or 10 layers deep, so simply because if the number of directions, think about this, right? If I randomly flip a coin and 3 times, randomly roll a dice, and 1 time out of 6, I multiply by a number greater than 1, and 5 times out of 6, I multiply by a number less than 1. What do you think will happen in the limit? Right? So, because each of them is different, right? So by the time you get to the 5th layer, this thing is going to vanish. This is for ELU activations. This is for ReLU. You can see that ELU activations maintain gradients for longer than for ReLUs, right? For sigmoids, the gradients are the derivatives vanish even more quickly. For tanh is slightly better than sigmoids, but not very much, right? This is for batch, for an entire batch. If I look at individual instances, I see much the same pattern. What we find is that by the time we get, ELU activations maintain the gradients longest, but in all cases, the gradients effectively vanish after about 10 layers. And this is both for over the batch, where you would hope that the accumulation of gradients across many instances will give you something significant. It doesn't. And also for individual instances. Now, the fact is that not all gradients are going to go to 0. There will be a very small, tiny fraction where the gradients are really blown up, but you can't really see those because they're so small in number. And so what we find is that as you go back deeper and deeper, this one was These were 9 individual instances, 9 individual training sets per annum. Here, this was a tanh activation sigmoid ReLU for batch gradients. And this is for individual gradients. Did that answer your question, Varhana? Okay. So in both cases, the gradients vanish or disappear, right? So we have this business with vanishing or exploding gradients. So the story so far, recurrent neural networks retain information from the infinite past in principle. In practice, they are poor at memorization. The hidden outputs can blow up or shrink depending on the eigenvalues of the recurrent weight matrix. The memory is also a function not just of the eigenvalues of the recurrent weight matrix, but also the activation of the hidden units. tanh activations are the most effective at retaining memory, but even they don't hold it very long. And so deep networks in general also suffer from vanishing or exploding gradients because the gradient of the error at the output gets concentrated into a very small number of parameters in the earlier layers and goes to zero for others. This making sense? Lesson so far. Okay. I'd like to see some thumbs ups. Okay, the last one. So Mariam, what do you mean? Which last point did
the gradient of the error at the output gets concentrated into the small.
So what happens? Like I was saying over here, right? So the gradient is going to shrink in most directions. And it's going to expand in just a small number of directions. Correct. So this effectively is going to be, so direction is some combination, but it's going to be dominated by a small number of neurons, and most of the neurons, you can think of each neuron as a statistically independent operator, right? So that's basically what this means. Did that answer your question?
I was mentioning about, can you go on the slide again, the last one, the so far story?
Okay.
So like saying the oh, okay. Yeah, got you. But like the earlier layers, I don't get why on the earlier layers.
So this is earlier layers is like the lower layers, these guys.
Oh, okay.
That makes sense?
I see. Yeah, thank you.
Okay. So we use you used ReLUs, you used residual networks. If you didn't use ResNets, you'd run into these issues. ResNets were specifically designed to avoid this problem by having the residual line over which the gradient never is just one. So, and now that was for general networks, but for recurrent networks are just very deep networks. This means that the derivatives of the error at time t are going to basically vanish or mostly vanish by the time you get to early in time. And so you will never be able to learn the behavior which says that something that happens here is going to influence something far away in the future. But then, and so, right? And so we have this issue. We have trouble learning things. You have trouble remembering things. Things disappear even going forward. And both of these are not things you want. So here's another point. If the gradients are clipped, Ahmed, that means that it's going to get worse, right? Because the things that you don't have a floor on the gradients, you're just trimming the things that became too big without doing anything about the things that died. So it's going to get even worse. Did that answer your question? Ahmed? Yes, no? Yes. Okay, 5 seconds, guys. I'm sorry for terminating the poll so quickly, but we're running out of time. So yeah, let's just go through this. For the first poll, the derivatives for most parameters will become vanishingly small as we back propagate the loss gradient through deep networks. True or false? Second one, the derivatives for a small number will blow up and become large and unstable. True or false? Right? The derivatives would be more stable if the recurrent weight matrices had singular values that were all equal to 1. True or false? Right, because the reason they were blowing up was that the singular values were either greater than 1 or less than 1, right? Similarly, if the activations were all identity transforms, the derivatives would be more stable. True or false? Right. So same thing. That was for the derivatives. What about the memory? The memory of the recurrent layer is limited because recurrent weight matrices are not unitary. True or false? Right. Because if you have any eigenvalues that are greater than 1 or less than 1, some things are just going to die. Correct? So the memory is also limited by nonlinear activations. True or false? Right. And so the memory would be more stable if the weight matrices were identity matrices. True or false? Right? Because now it's not going to be shrinking or expanding things based on the vagaries of the weight matrix. And the memory would be more stable if the activations were identity transforms. True or false? Right? Because we saw the sigmoid, the ReLU, the tanh, all of them mess with the memory and cause it to saturate, right? Yes or no? Okay, so let me move on, right? All of these were true. But then here's what you have. We actually need long-term dependencies. What is the kind of memory behavior we really want? Let's say you're using the recurrent neural network to parse code. If you're parsing code, then once you encounter an open brace, you have to remember that an open brace was opened, that this brace was opened until the brace is closed, regardless of how much other code happened in between. So you want the things in memory to stay there until you get a trigger in the input that this can now be forgotten. Is this making sense? Right. So the memory behavior should be dependent on the input. I remember something, and I'm going to have to remember it till something in the input tells me, okay, now you can forget that because it's no longer required. How long I remember something should not depend on the parameters of the network. It should depend only on the input, right? So how can we do this? For that, let's get into, mystery and magic, LSTMs. Let me go back here. We have this issue. The memory is affected by these W's. The memory is affected by these F's. The ability to learn is also affected by the W's and by the F's. If I don't want the memory to be affected by W's and F's, what's the simplest thing to do? What can I do? Just the presence of this weight matrix is causing me grief. Just the presence of an activation is causing me grief. So what can I do? Any suggestions? Get rid of them, right? Simply, I don't want this guy. This guy is causing me grief. Let me throw it out. I don't want this guy. It's causing me grief. Let me throw it out. But then if I throw it out, how do I modify what's in the input? What's in the memory? We can do that through some mechanism which modifies it based on analysis of the input. So we want a network that just remembers arbitrarily long And it's not dependent on the vagaries of network parameters, but rather on input-based determination of whether whatever is in the memory must be remembered. And for that, we're going to replace this with something that doesn't fade or blow up. We're going to use something that's based on switches. This modification no longer has any waits or activations. Something in the memory is going to, if I encounter something at time 0, I stuff something in memory, and thereafter it's going to be modified based on analysis of further inputs. Going back to this example, once it encounters the curly brace, it's going to store it in memory. And then as each additional character comes in, it's going to keep looking at them, and only when it finally finds a closed brace that closes this guy is it going to delete this thing from memory. That's what we're going to do. And so this switch is a switch that analyzes the input and modifies the memory. So that gives us the structure called the constant error carousel. C is the memory. The C goes through straight in time. It's not, it has no waits, it has no activations. At each time, however, whatever is in the input is analyzed, and there's a switch represented by the sigmoid, which modifies what's in memory based on what it sees in the input. Is this picture making sense? C is a function, whatever. This is C of T is what is in the memory. It's just the memory. Right? That answer you, Mariam? I'm just calling whatever is in memory as C of T. Okay. So this makes sense, right? Based on what we've just seen. But then how do we modify this? First, the thing is you want nonlinear stuff. Not really, because you have things modifying it at a one. So anyway, we want nonlinearity because in a neural network, the actual work is done by the nonlinear activations. So we're going to keep things in memory in this manner, but to use it, we're going to put whatever is in memory through an activation function to get the actual hidden state. And what is this gate which modifies here? The gate is going to look at the current input, but also what is currently in memory. There's no reason to be modifying a memory line which is counting the number of curly braces if there isn't already a curly brace over here, right? So it's going to be looking at the input and saying, I saw a closed brace. I also know that there's an open brace in memory. So I must modify what's in memory. So it looks at what's the decision of the switch must depend based on both on the input and what's actually in the memory. That making sense? Rest of you guys, this making sense? Right. So, and of course, you want to consider other things like the context. Is this in a comment section? A closed brace in a comment section should not count, right? And of course, you just looking at this non-linearly transformed version of the memory is not enough. So you may also want to add a direct line from the memory itself. But these are all the inputs that the gate could consider before it decides whether to modify what's in memory. Is this picture making sense? Yes, no, give me a thumbs up if it is. Guys, can I request you to give me a thumbs up? I'll wait for 25 of them. I have 22. I need 4 more. So give me a few more thumbs ups, please. You counted down instead of up. Well, it's okay. Let me continue. The next time, please do. So this gives us the so-called long short-term memory model. This explicitly latches information to prevent decay or blow up. And in the slides that follow, I've borrowed heavily from this Cola GitHub for the pictures. Now here's your standard recurrent neural network. You have the input and the hidden state at the previous time. These are combined and analyzed by an activation. Typically, we use a TANH because a TANH remembers things for the longest time. And the output of this is passed on to the hidden layer the next time and also deeper into the network. This is the standard recurrent network. This entire operation can be thought of as a cell. What happens at one time in a standard recurrent network? Is this making sense? This picture? Yes or no? Okay. And now this guy gets modified to this one in the LSTM. And then if you look at this, you're going to wonder, whoa, what was that? So let's see what is happening over here, right? One by one. First is this basic line called the constant error carousel, which is a remembered cell state. Again, remember that each line is actually a vector from our original pictures, right? There are many lines. So this is several activations, an entire layer of activations. So this is what's in the memory. It goes through and it's not modified by any waits or activations. It's only modified by these two operations, which can change what's in the memory. So let's continue using the open and close braces example. This could be remembering, for instance, that I've seen 8 open braces so far. Then the first way it's modified by these two units. The first one is something called a forget gate. So by the way, these gates, they're all simple sigmoidal units. They have the property that they can only shrink. They multiply whatever is going through by a value between 0 and 1, because sigmoids only generate values between 0 and 1. And so they cause these values to shrink. And the first gate over here is a so-called forget gate. And it tells the memory whether it must forget some of what it remembers. So for example, if this guy is carrying the number of open braces, I've seen 16 open braces, then this one here is going to analyze the input and get input and other things from the memory and decide whether it has seen a curly brace, closed brace. And if it has seen the closed brace, whether that means that this count must be decremented. And so that's what this gate does. Is that making sense? Yes or no? Thumbs up, thumbs down. I'll wait for 25 thumbs ups now, please. I see 3. 16, 17, 18, 19, only 20, 50. So I see 1 thumbs down. Who's the thumbs down? I only got 20 thumbs ups, guys. Many of you are not paying attention. Who's the one who had a thumbs down? Can you explain your request? What was unclear? There was one person who didn't get it, right? So, okay. Then let me just repeat. This one looks for triggers that must decrement what's in memory. So if, for example, the memory says I've seen a certain number of open braces, this would detect patterns like closed braces. And if it detects them, it's going to decrement what's in memory, but it's going to do it multiplicatively. Now, the second guy is what's in memory. You don't just decrement what's in it, you also want to increment it. So this guy has the job of incrementing what's in memory. First, if this guy is opening curly braces, counting open curly braces, this one is going to detect more open braces. So this first thing is a pattern detector, which looks at the input and the current hidden state and determines if the pattern is something that could potentially increment this guy. So this is a pattern detector, C tilde T, right? But then the detected pattern is influenced by the context. For example, that pattern could be in a comment block, in which case seeing an additional open brace in a comment block should not modify what's in memory. So to control that behavior, you have a gate over here. This is a basic pattern detector, and this is a gate which determines how much of the pattern that's detected must be accumulated into the memory. So this is called an input gate, just as this was a forget gate. The input gate controls whether a pattern that has been detected will modify what's in memory. And what's in memory itself is decremented multiplicatively by this forget gate and incremented additively by this pattern detector. You're probably going to wonder why a multiply and an add. Why cannot both be adds, or why cannot both be multiplies? If you make both of them the same operation, then they become non-identifiable. You won't be able to say which is which. And so you can get confusing behavior. But we have two distinct operations, an increment and a decrement. And so we have two different operators, a multiplication for the decrement and an addition for the increment. Does this make sense? So to answer, how do I know what each is doing? The fact that, let me go back here. This guy only generates an output between 0 and 1. So the only thing it can do is to decrease what's in memory, right? Lehan? So this is forgetting. And this guy is additive. So it could increment or decrement, but mostly it's going to be, it's an additive increment of what's in the pattern. Now, finally, what's in the memory must be non-linearly transformed. So that nonlinear transform, exactly, Kishore. It's like saying, I found an open brace, but this happened in a comment section. So because if it's a comment, I shouldn't really be adding it to memory. So that's what it's controlling. It's limiting what is added. And the hidden state is actually put through a nonlinear activation, a tanh, because tanh are what we use on the recurrent layers of RNNs, as we saw. And that output in turn is modified by something called an output gate. I have never really seen why we need an explicit output gate of this kind, but empirically it helps. And so this is the non-linearly transformed version of the memory. And so here's the, and of course, all of these gates get inputs from the direct input, the non-linearly transformed version of the memory, and the direct memory itself. This is what they call a peephole connection. So, Yuyun, so for example, again, going back to the curly braces, if I find an open brace and I detect a curly brace, a closed brace, what must I do with the memory of the open brace? What would you do, Francis? You'd forget it, right? So for example, if you're parsing code, you keep counting the open parentheses, open braces, and every time you see a curly closed brace, you forget, or you forget one of the open braces that you saw. That's basically what it's doing, right? So the output over here is just put through a nonlinear transform, the tanh, and there's a gate that's sort of used to modify it because why not? That's all. At some point, it got too complex as far as I can see. And so here is the entire LSTM structure. You have the memory line. Okay, let me actually go through this poll. Jessica, yeah, this is just Zoom messing with you. I'm sorry about that. So, guys, I'll stop this poll early because we are running out of time. So I'll end the poll, share the results. Here's what everybody thinks. And can you tell me, is this first statement true? LSTM stabilized the memory by eliminating the problematic recurrent waits and activations. True or false? True, right? They update the memory based on patterns detected in the input. True or false? True, right? In the absence of external cues, now they can remember a pattern forever. True or false? True. So they are suited to building pattern analyzers requiring long-term memory. True or false? True, right? Okay. So all of them are true. So here is a complete set of operations. You have the C and H coming in. And first you compute the forget gate. Then you compute the input gate and the pattern and the actual pattern. So here's the order of computation, right? You compute the forget gate and the input gate and the patterns. Then these three are used to modify what's in memory. The forget gate scales down what's in the memory, and then the combination of the pattern detector and the input gate increments it. And now the modified memory is what is used to compute the output gate, which then which then multiplies the non-linearly transformed memory. It looks complex. There's a little bit of redundancy in it, and there was a lot of work in the literature on trying to simplify this model. So I have some pseudocode over here for it. You can just look through the pseudocode to see how it's actually implemented, each step. Now, training the LSTM is identical to training the regular RNNs with one difference, that instead of backpropagating gradients through an RNN unit, you'll be backpropagating them through an LSTM cell. And that's horrible, right? Look at the two adjacent time steps. So Yulin, the input gate is multiplying this pattern detector. The forget gate is directly multiplying the memory. So that's why they will behave differently. That answer your question? Yeah, okay. And so let's see how derivatives come down. We can determine how CT plus CT minus 1 influences the divergence through this line, right? Through this line, through this direct line, through this line, through this line. So if you try to do any kind of analysis using the influence diagrams we drew earlier, you're going to find this gets very, very complicated very quickly. Similarly, let's see how this HTs, how the HT influences the divergence through this line, through this line, through this line, through this line, right? And it gets very complex very quickly. So clearly, trying to write out the math for this is going to be quite hard. Instead, I'm leaving this as an exercise if you feel masochistic, but it's much simpler to look at it in terms of code. And your homework will actually show you how to do this using code. Now, do you guys have 5 minutes to spare? Because in that case, I can spend a little time just over this, okay? So here's what the forward computation did. In the forward computation, you first computed the affine value for the forget gate, then put it through a sigmoid to get the forget gate value. You computed the affine term for the input gate and then put it through a sigmoid. Then you computed the affine term for the pattern detector and detected the pattern. And so the memory was modified by multiplying what was already in memory by the forget gate and then adding to it the product of the pattern detector and the input gate. Then finally, you computed the affine term at the output gate and put it through a sigmoid. And this output gate multiplied a non-linearly transformed version of what was now in memory, right? And that's what we've returned. So backpropagation is going to go backwards. So let's see what happens over here. This is what it's going to go. The last operation over here was this one. Let's see. So H equals O multiplying tan H of 0, right? This is what we will invert. I'm assuming that when I'm coming back in, the output, the derivative of the divergence with respect to both C and H, which is what went out of the cell, are available. And so just looking at these two guys, I have DC and DH. So inverting this, I can say that DC is going to be, so DO is going to be D tan HC. Sorry, no. DO is going to be DH times tan HC, and DH is available, right? You can see how I just wrote this backwards. Then this one, if I thought of it as a variable, D tan HC is simply going to be DH times O. So do you see what these three guys are right here? these three terms. I have the derivative for H and C, right? So I have H equals OC, O tan H. I have DH. So the derivative of O is going to be DH times tan. The derivative for tan is going to be DH times O. That's all. This is the same rule that we saw earlier. This making sense, guys? Yes or no? Right. And then I have the derivative for tan H. So from the derivative of tan H, I can actually, I can compute the derivative for C, just using the standard derivative rule for tan H. So I basically use the same computation going backward for every single operation that I perform going forward. Eventually, I have computed the derivatives for every term inside the cell. I suggest that you go through these slides, but better than this, there's actually a slide deck that we're handing out on how to compute a derivative. Take a look at it and it will explain things very cleanly. It's part of your homework. Now, one thing you might have wondered, why have a separate H line, memory line and an H line? Lots of others have wondered about it. And so there have been various modifications to the LSTM unit, like the GRU, which tries to get rid of that by being a little more logical. This one combines the input and forget gates, doesn't bother to maintain separately maintain compressed and regular memories. And there have been other variants. And also to round off now, these cells would now be LSTM cells instead of RNN cells. That's all. And you can do this, you can use them both in forward and both in unidirectional and bidirectional networks. So the story so far, I rushed through the last bit, but did this make sense? All I did was to replace the cell with an LSTM cell. What about the rest of you, right? So that's it. And so the story so far, recurrent networks are terrible at memorization. Memory can explode or vanish depending on the weights and activation. They suffer from the vanishing gradient problem during training. The error at any time cannot affect parameter updates in the two distant parts because of this vanishing gradient problem. And so, for example, what this means is that seeing a closed bracket cannot affect its ability to predict an open bracket if it happened too long ago in the past. So if you're wondering why the vanishing gradient problem is an issue for recurrent networks, this is one, right? LSTMs are an alternative formalism where the memory is made directly dependent on the input rather than network parameters and structure through a constant error carousel memory structure with no weights or activations, but instead direct switching and increment from pattern recognizers. They do not suffer from a vanishing gradient problem, but they do suffer from an exploding gradient issue, which you can deal with things like clipping and so on. So we've covered the basic idea of recurrent neural networks. The big issue is, how do you compute this divergence between sequences? And how do we use that to train the network? How do we use these networks in general? What can they do? This and more in the next couple of classes after the break. I'll stop here. Any questions?